Chapter 1 is going to be a chapter that contains topics you may have discussed if you've taken a science class before. But we want to make sure that everybody is starting at the same point. So we're going to talk about an introduction to matter, measurement, and problem solving. It is really important to make sure that you understand the topics in this chapter because future chapters are going to build off of them. It's also important that you try the material on your own. I know that when I'm working through problems, and this happened for me as well when other instructors, when I was taking classes, would work through problems, everything made sense. But as soon as I left and tried them on my own, I would get stuck. So make sure that you try practice problems so that you know and are confident that you understand the material. I'm happy to answer any questions that you may have on the material as you work through it. So let's get started with the composition of matter. We're going to start with atoms and molecules and define what those differences are. So we have two examples here of molecules. Okay, so on the left, we have one carbon and one oxygen atom. Okay, they're atoms because atoms are individual units. And when they attach to each other, they then become a molecule. So because there's more than one atom and there's a physical bond between them, it becomes a molecule. So on the left, one carbon, one oxygen. We'll learn more about naming later, but this is carbon monoxide. On the right, we have two oxygen atoms and a carbon atom that are physically bonded to each other. And this is carbon dioxide. They have very different properties. The only difference is one oxygen atom, but carbon monoxide is deadly if inhaled in large quantities because it can bind to hemoglobin replacing oxygen. And our body can't use the carbon monoxide in order to power the cells. Carbon dioxide we exhale on a regular basis as a result of respiration. So let's look at some formal definitions of atoms and molecules. So atoms are submicroscopic particles, so we cannot see them with a light microscope. They're fundamental building blocks. They make up everything around us, either individually or when they are combined into molecules. Molecules, on the other hand, are when we take two or more, and some molecules are very, very large, like the proteins in your bodies. We have thousands of atoms attached to each other. We have two or more atoms attached together, and they make a very specific arrangement. And we'll learn more about how and why they bond or attach to each other in the way they do in future chapters. Okay, they do come in different strengths, and we'll learn about the different strengths of bonds. So we have things like ionic bonds and covalent bonds, and they bond in different shapes and patterns. So in our example of carbon monoxide and carbon dioxide, notice that they looked very linear, or one atom attached to another. In other molecules, they're not as linear. And again, this is something that we'll learn about in later chapters as to why and how and the shapes that they take. And so when we're studying chemistry, really the goal is to figure out and understand the behavior of why these atoms behave in the way that they do. And so we're talking about matter, and matter is everything around us that takes up space and has mass. And so matter is made out of atoms and molecules. So if we understand the behavior of the atoms and molecules, that allows us to understand the properties of the matter around us as well. So basically, chemistry is studying everything around us. We're just thinking on a very, very small scale. So remember we said submicroscopic. Okay, smaller than what light microscopes can see. So I do like to throw in a few little cartoons or memes on occasion. So this is one that I really I think is funny, but never trust an atom. They make up everything. So because everything around us is made of matter, even the air, even though we don't think about air containing molecules, it does. It contains nitrogen, carbon dioxide, carbon monoxide, oxygen. And so even the air is made up of matter. So and as chemists, we do like to put things into categories. And so we are going to talk a little bit about how we can classify the matter. So talk about different states of matter. We're also going to talk about physical and chemical changes that occur. Okay, so what exactly is matter? Well, matter is anything that takes up space and has mass. And so unless we are on planet Earth, unless we are dealing with a ultra high vacuum, we do have matter present. Okay, we still have air, or we still have gases that are present, and so it takes up space, it has mass. And as I alluded to, there are some different ways that we can classify this matter. So one is the state. Okay, so the state is whether it exists as a solid, a liquid, or a gas. And we can talk about it at room temperature. We can talk about it at different temperatures. And so we know that if we change the temperature, we can also change the state. When we think about a solid, think about what type of properties solids have. And how is that different than liquids and gases? Well, solids have a defined shape and a defined volume. Okay. When we talk about liquids, they have a defined volume, but they take on the shape of whatever container they're in. And the gases, they have no defined shape. They also have no defined volume. They will fill whatever container they have, okay? And they'll take the shape of the container. Now, if we look at the individual, in this case, atoms in our picture, okay, we can see that as a solid, the molecules are very they're in a defined position. So they have very little freedom of motion. Okay, now they're still vibrating, okay, but those positions are kind of fixed. When we move into a liquid, we have more gaps and spaces between the molecules. So there's spaces. And so the molecules are able to slide past each other. And this is what leads to the properties of liquids, because they have more freedom of motion. They can slide past each other. And that's what defines the property of liquids. When we get to a gas, we have the most freedom of motion. Okay. There's a lot of space between the molecules, and that's also what leads to gases being able to be compressed. So we can squish the molecules closer together in a gas. In a liquid and solid, that's not possible. We can also talk about its a matter's composition, or what makes up the basic components of that matter. And we can classify those even further. Oh, first though, okay, I know it's a silly meme. I apologize, but thought I'd throw it in there. Okay, so if we're looking at the composition, we can break it down into what makes up the matter. Okay, so we have pure substances, so made up of only one type of individual particle. It is a pure substance, and its composition does not vary. So if we're looking at one sample to the next, it's going to stay the same if it's a pure substance. If its composition can vary, if we can change it looking at sample to sample, then it is a mixture. Okay? And mixtures are made up of more than one compound or molecule. Okay? More than one pure substance that is combined together is a mixture. If we're talking about an pure substance, we can break that down further as well. Can we separate it into something simpler by chemical means? So can we break it apart further? If we can't, then it is classified as an element. So an example of that would be helium. But we can look on our periodic table, and there are lots of different elements that are possible. Okay. If there is more than one atom attached to each other that are different than each other, so in an example of our pure water here, it is 2 hydrogen and 1 oxygen. So we have 2 different elements, and they are physically attached to each other with a bond. Okay, so there's each one of these is a molecule of water. It is still a pure substance because each molecule is the same as each other, or as the same composition as the ones around it. Okay, but all of those molecules have the same components of 2 hydrogen and 1 oxygen. Okay, if we look at helium, for backtracking a little bit into elements, helium just has a single element. Now we can have molecules that are elements. For example, nitrogen, when it's found in nature, is 2 nitrogen atoms attached to each other, but they are the same element still. Okay, so it's 2 of them, but they're the same element, whereas our water, we have 2 different elements. Okay, let's talk a little bit more about mixtures. We can break these down, okay, into different categories. And is it uniform throughout? Okay, another way that we can think about it is, can it be separated through physical means? Okay, so mixtures can be separated by physical means, where pure substances can only be separated through chemical means or by chemical reactions. Okay, physical means that we can heat it up, we can cool it down, we can filter it, things like that. Okay, so if there is a uniform throughout, that's what we call a homogeneous or homogeneous mixture. It looks as if it is one substance. Things are evenly distributed, those different molecules. So here in this case we have tea, we've got some sugar molecules, we've got some water molecules, there's other flavoring in there as well. So we have individual different molecules that are combined together, but they're combined in such a way that it is uniform. Okay, so it's evenly mixed. No matter where we take a sample in that mixture, we're going to get the same amount of sugar and water. If it is not uniform throughout, then it's heterogeneous. Okay, so depending on where we take our sample, in this case we have wet sand, we might end up with more water molecules, we might end up with more sand molecules. Okay, so it is not a consistent composition. Okay, depending on where our sample, even though it's the same sample, depending on where we take a look, we see different components in our mixture. Okay, so we were talking about chemical and physical means. So let's look at physical changes. So physical changes, they change the state, they do not change the composition. Okay, so we don't change the composition. That means that we're not breaking chemical bonds and forming new molecules. The molecule itself remains the same, even though it changes. So things like state changing, boiling. So boiling is when we go from a liquid to a gas. Okay, that's boiling. Condensing, we go the other way, gas to liquid. Those would be a physical change. Melting, okay, we're going from solid to liquid. Freezing, we go the other way, liquid to solid. Okay. All right, subliming is one that we don't frequently see. Okay, but subliming is when we go from a solid to a gas directly without the liquid state in between. Okay, depositing, and so an example of subliming would be dry ice, as we can see on the right. Dry ice will go directly from a solid into a gas, but notice the molecules do not change. Okay, so they have less freedom of motion in the solid. When they sublime, there's still carbon dioxide, but now they are in the gas form. They have more freedom of motion. Okay, deposition or depositing is gas to solid. And you may have noticed sublimation or subliming if you've left ice cubes in the freezer for a very long time. You'll notice sometimes that those ice cubes shrink. Okay, they haven't melted because the freezer hasn't warmed up, but some of those surface water molecules will escape into the gas phase. Another physical change is dissolving. So dissolving, the sugar molecules, they remain as sugar molecules, but now they're surrounded by water. Okay, so we haven't changed the composition, we haven't broken any bonds, okay, but we've changed what the substance looks like. Okay, and we can reverse physical changes by reversing what we do. So or we can get back our original components. So if we dissolve something, we can heat it up, we can evaporate the water, we'll get the sugar back. Okay, if we boil something, we can collect the gas, cool it down, we'll get the liquid back. So they're reversible processes, easily reversible. Okay, common chemical changes. Now we're going to break bonds. So we're changing the composition. We're breaking bonds, forming new molecules. So an example of this is rusting or burning. So we're breaking bonds, we're undergoing chemical reactions in order to form new bonds. So for example, burning, we're taking, in this case, propane. We're adding oxygen. We're forming new molecules of carbon dioxide and water. The bonds are physically breaking apart, forming new molecules. Another one is dyes fading or changing color. That actually changes the composition of the molecules. Okay, so let's see if you can demonstrate what you've learned. So here we have some different examples. So freezing water to make ice cube, dry ice evaporating at room temperature, toasting a piece of bread, dissolving sugar in hot coffee, crushing an aluminum can. Which would be a chemical change? Take a minute, think about that. Which would be a chemical change? Well, our chemical change, freezing water to make ice cubes, we're changing temperature, so we're changing state, but it's still water. Dry ice evaporating, again, we're taking carbon dioxide from the solid form, moving it into the gas form, but it's still carbon dioxide. Toasting a piece of bread is our chemical change. We are actually undergoing a chemical reaction where we take the proteins in the bread, reacting it with heat, and you'll notice a color change that occurs. This is undergoing something called the Maillard reaction, and so we're breaking bonds, forming new bonds through toasting a piece of bread. Dissolving sugar in hot coffee, again, this is dissolving, so the sugar is still present. It's just now surrounded by the water that's in the coffee. And crushing aluminum can, we're changing the shape of it, but it is still aluminum.